Chapter 3, Vectors. Some of you may have seen vectors before, depending on which part of the calculus series you're in, or you may be about to see vectors, again, depending on how much calculus you're going to take. This chapter is really a mathematical chapter to cover the tools we need to describe vectors, because lots of physics uses vectors, this mathematical concept, in order to analyze the world around us. So the first section is taking a look at vectors and their components. So first off, what is a vector? Well, it's not just some sort of virus you can catch. In this context, it's a mathematical object that has size and direction. Those are the two keys. So a vector quantity is something that can be represented by a vector, something with size and direction. So position, velocity, acceleration. Those all have an amount or a size, but also a direction associated with them, where the velocity isn't just that you're going 60 miles per hour, but you're going 60 miles per hour north. Now it's a vector quantity. And the reason we care about vectors is they have their own rules for manipulation. It's much more involved than when we have scalars or simple numbers. So scalar is any quantity that does not have a direction. It's basically just a number with a unit. So time, temperature, energy, mass, these are directionless, but they do say, time has units of seconds. It's been 60 seconds, or a temperature of 100 degrees Fahrenheit, right? There still are units here, but there's no direction. And as a result, it can be manipulated with ordinary algebra. So scalars are a lot easier to work with. And we'll actually look for techniques to represent vectors with scalar quantities, because the scalars are so much easier to work with. All right, but for now, let's first take a closer look at vectors themselves. So the simplest example of a vector would be a displacement vector. A displacement vector, so it could be if something changes position. It goes from point A to point B. It has been displaced that distance, right? And so we could represent that by a vector arrow that points from point A to point B to say, hey, whatever this particle is, it went from A to B. Cool. And all three of these arrows actually are identical vectors because they have the same magnitude and the same direction. So we're able to freely shift our vectors. If you picture this as a vector, we can transpose it up, down, left, and right, as long as we keep the direction the same and as long as we don't change the length of it or the size of it. Another interesting point is the displacement vector, we remember, only cares about the endpoints of the motion, right? It only cares about where you started and where you finished up. So it doesn't matter how you got from A to B. So you could have taken a curvy path to get from A to B, or you could have taken this really roundabout path to get to point B. But they all correspond to the same displacement vector, which says, okay, the net offset in distance traveled was from A to point B, and all the distance covered is irrelevant. So we don't actually care about the path. Right, now the vector sum is if we want to add two vectors together. So this is vector addition, and so it represents the net displacement of having two or more vectors, right? So you could say you start out going from A to B, and then you go from B to C. Well, where do you end up at the end? You end up at the very tip of point C, and that's what this is showing. Maybe the actual path is in red, but you somehow get to point B, so the displacement vector is that direct straight line, shortest distance between the 2 points. Similarly, you follow a meandering path to get to C, and we can draw the displacement vector of your path, which is the straight line connecting B to C. So our net displacement is from the original starting point to the final finish. It's the vector sum. So if we call this vector S, it's equal to following paths A plus B. They get you from the same starting point to the same finish point. So we can add our vectors graphically, it turns out. The way to add them is we'll need to be very careful about the alignment. So we're always going to want to treat them, I like to think of it as displacement vectors, right? So if I'm adding A plus B, then I'm going to focus on starting at A following it here and then saying, okay, now B is my next direction. So I need to line B up so that I can then follow B to the very end of it. This is called lining it up tip to tail, where the head or the tip of A is pointing to the tail of B. This is the first step in vector addition. To get the resultant or the vector sum, you go from the original start point, wherever you were to start, and then you draw the vector to the final head, to the final finish. So that's why vector S is drawn from that original start point and then pointing towards that final finish. All right, so some other notes on vector addition. First off, it's commutative, so you can add the vectors in either order. This is one of those things that seems kind of intuitive, but also kind of not when you think about it visually. You'll get the same result if you follow path A and then path B, as if you had instead followed path B of going down into the right first, and then followed path A of going up into the right. Either way, you'll get to the same finish point. Pretty remarkable. Another interesting fact, or maybe not so interesting, but I think it's interesting with vectors, is it's associative. So we can group the vector addition however we want. We can add it in any number of groupings. So here's adding vector A with vectors B plus C grouped together. But we could also add, let's see, vector A plus vector B plus vector C. And the resultant would just be this purple A plus B plus C. Or we could add vectors A and B first, which is shown here, and then add the A and B to vector C, and we get the same resultant. Either way, we get this resultant that is shown in purple, no matter which grouping of vector addition we do. Now, how do we reverse our vectors or deal with subtraction or negativity? There's lots that can pull us down in this world. Well, it turns out a negative sign will reverse the vector's direction. So if we start out with our vector B pointing up and to the left, negative B is going to point the exact opposite direction, down and to the right. In that way, vector B plus vector minus B is equal to 0, which we can see here. We start at the start of B, we go out, then we come back, right back to where we started, 0 displacement. So this is what we use to define vector subtraction. Rather than thinking about trying to subtract things, which is hard, we instead define vector subtraction A minus B as A plus a negative B. So if we're adding or if we're subtracting A minus B, we're going to need to find the minus B direction. So minus B is flipped, it's pointing up in this picture instead. And notice now, the way it's drawn, we have two heads pointed towards each other, so we can't draw a resultant yet. So this is where we would need to shift one of them, and you could shift either one. So they shifted the A, which we could show, that you could shift the A down so that the tip of A is pointing to the tail of B, or of negative B, excuse me. But you could similarly shift negative B, right? So I could have shifted minus B up here, and that would be the equivalent as well. Either way, the final resultant is going to go from the original start point, whichever one this is, to the final arrow finish. And in all three of these blue arrows, they're the exact same size and direction. They're the same vector. All right, and so these rules will hold for all vectors. Here we focused on displacement because that's the easiest to sort of conceptualize, wrap our minds around, but it will also be true for velocity and other vectors we can see like force. One note is only vectors of the same kind can be added. So we can add a distance with another distance, and that would make sense, but it doesn't make sense to say I walked a distance of 4 meters north and 3 meters per second east. It's like, wait, you can't add those two because one of them is a distance and one of them is a velocity. It just doesn't work. All right, so let's look at a checkpoint, see how things are going with this. It says the magnitudes of displacements A and B are 3 meters and 4 meters respectively, and vector C is A plus B. Considering various orientations of A and B, what are A, the maximum possible magnitudes for C, and B, the minimum possible magnitude? So I want you to think about this, write down answers for both A and B here, and we'll check in just a moment. So go ahead and pause now. Did you do it? Okay, I'm gonna hope you did. Gonna have to trust you there. All right, so we have A and B, and A we know is 3, and then B is 4 meters. So if we want to find the maximum possible magnitude, as we're thinking about these two vectors, how can we arrange them considering various orientations? If we let them rotate in whatever way we wanted, which way would produce the longest possible resultant vector of adding the two? Well, we're going to get the longest possible if they are working together in exactly the same direction, right? If vector A is pointed one way, vector B is pointed in that same direction. And in that case, how long would that be? Well, that's just the full length of each of them added together. So that would have to be 7. Think for a moment about the minimum possible then. It's easy to jump to 0 because we think of 0 as the minimum, or perhaps a negative number, but it says magnitude, and negative would just be a direction. So magnitude is the smallest possible size. And so if we think about rotating these to various orientations, we know when they're in the same direction, that produces the largest resultant. Then they're somewhat working together, then they're somewhat working apart, pointing in opposite directions until they're completely diametrically opposed, pointing in opposite directions. In this case, if we arrange them so that we have 3 meters going one way, 4 meters going the other, then they are going to nearly perfectly cancel out. Not quite perfectly because they have different magnitudes. There will be a little bit left over. How much? Should be 1 meter. So that walks you through some of the ideas there on finding the maximum possible length that we could have in adding two vectors and the minimum possible length that it could possibly have. This is an interesting one, so if you have questions, please ask. I would love to discuss it further.